The kinematic robotic arm neural platform consists of complex mathematical algorithms developed with Python, Java, and C++. The main objective is to provide the autonomous control engineering environment for motors, sensors, visual cameras, and gyroscope sensory technologies. The kinematic robotic arm manipulator makes use of several complex mathematical algorithms. The scope of this framework is to show the implementation of Quaternion Kalman algorithms, fast Fourier transform algorithms, and sensor control obstacle algorithms. The main objective is to provide engineering solutions to robotic kinematic arm manipulators, as illustrated in this specific design. I also used the dynamic path planning algorithm to enable the robotic arm manipulator to sense the presence of obstacles and to identify the points of the body that are physically or proximal contact with the obstacle. The objective is to design and develop kinematic algorithms for the control of sensory robotic systems. The kinematics is solved in the sensor coordinate. Thus, simplification of the algorithms is done when approximations are used to solve the inverse kinematics. The kinematic method is based on the resolved motion rate control, in which the required velocity of the end effector is related to the joint variables. 6 joints are required in order to position and orient the end effector in space. The kinematic robotic is characterized by the use of algorithms of reading points of 3D space, floating interpolation by a polynomial of the 5th order, iterative process of solving inverse kinematics tasks, dynamic feed-forward torque of each motor, and calculation of position control algorithm with a control loop. The sensor is able to produce 3 components of the required linear velocity of the TCP in 3 orthogonal axes, and 3 components of the required rotational rates, such as angular velocity about this axis. These technologies are used by industrial robotics for equilibrium, balancing, as well as orientation purposes. The fast Fourier transform is a mapping of data between 2 domains. Using zero-based indexing, x of n represents the nth element of the input, and x of k represents the kth element of the output. X denotes the signal level at various points in time, and x denotes the signal level at various frequencies. The signal level at frequency k is equal to the sum of the signal level at each time n multiplied by a complex exponential. fast Fourier transform algorithms. The objective is to develop and implement fast Fourier transform algorithms for the discrete motion group of the plane. These FFT mathematical algorithms apply fast Fourier transform methods to the computation of convolution-like integrals that are endemic in robotic, kinematics, and motion planning. Fast Fourier transformation, FFTs, is a mathematical module that samples signals over a specified time segment. It measures every cycle that would include different variables of the system. FFT algorithms in robotics. Here I focus on the problem of computing the workspace density function for discretely actuated link revolute robotic manipulators and variable geometric truss manipulators. The robotic kinematic artificial intelligence generates the workspace density for the discretely actuated M-link planar revolute manipulator. Each link has one of n orientations relative to the previous link, and the length of each link, L of I, has a fixed value. The kinematic robotic arm generates the workspace density of a 6-link manipulator as illustrated in this video. It evaluates the signals detected by the sensors of a robotic architecture, such as vibrations from the surrounding and noise that is generated as the robot is at rest or in motion. This will disrupt the environmental and the system functioning network. Real operations requirement in FFTs. A complex addition can be implemented as 2 real additions. Generally, a complex multiplication can be implemented as 3 real multiplications plus 5 real additions. In the case of the fast Fourier transform FFT, use of efficient radix minus 2, radix minus 4, or radix minus 8 algorithms can be used to reduce the number of non-trivial operations required. Thus, the computation requirement to implement the FFT and the training algorithm is given by a computational requirement to implement the FFT and a decision-directed adaptation algorithm. The computational requirement of an FFT, fast Fourier transform, is given by the equation n c MUT minus FFT is equal to n log 2 n over 2. Secondly, the number of complex multiplications and additions must be translated into real operations. Finally, the MIPS required must be calculated from the number of real operations required and the relevant parameters for each of the standards under consideration. Multiplications of real or complex numbers are very demanding. The complexity requirement is evaluated in 2 ways. In one case, only the multiplications are considered. fast Fourier transform mathematical models. A discrete Fourier transform can be computed using an FFT. 1. If the number of points n is a power of 2, or if the number of points n is not a power of 2. A transform can be performed on sets of points corresponding to the prime factors of n, which is slightly degraded in speed. The FFT algorithms fall into two classes: decimation in time and decimation in frequency. Cognitive computational control theory algorithms, also implemented. Homogeneous mathematical representation of artificial intelligent robotics. The transformation of points and vectors by rigid transformations has a simple representation in terms of matrices and vectors. The kinematics of the artificial intelligence open link manipulator is represented as a product of exponentials. A Quaternion-based Kalman filter fusing measurements gathered from robotic, kinematics, and inertial centers at different sample frequencies in order to estimate linear accelerations and angular velocities, accelerations of load. The recursive total process is executed to identify the load parameters. This frame of work presents the basic fundamentals from a system architecture. Some of the important technologies required to build a cognitive, thinking, artificial intelligence robotic system. Data fusion based on Kalman filter. A data fusion method based on the Kalman filter is described in this application. So you could see that the measurements of the accelerometer and magnetometer are used as the input of the two-step geometrically intuitive correction to produce the computed Quaternion. And the computed Quaternion is used as the measurement of the line Kalman filter in order to correct the predicted state obtained by using the output of the gyroscope. Quaternion Kalman filter for real-time estimation using geometrically intuitive correction algorithm. In this algorithm, the sequential geometrically intuitive correction is used to make the estimation of pitch, roll, immune to magnetic distortion. Meanwhile, the software algorithm produces a Quaternion input for the Kalman filter to reduce linearization, error of measurement equations. Developing thinking machines is a significant development and a great achievement. There will be philosophical theories, challenges, and social economical impacts caused by the development of artificial intelligence thinking machines.